So, a hypothesis is a statement about a population parameter. The goal of hypothesis testing is to decide, based on your sample, one of two complementary hypotheses, which one is true, either the null hypothesis or the alternative hypothesis. And so we'll just skip Bayesian hypothesis testing in 9.1 for the moment. We'll come back later. Section 9.2 is the frequentist approach called the Neyman-Pearson paradigm. And we start with a decision function, which is just basically a 0-1 function, whether to accept or reject the null hypothesis. And it's important to note that it's possible to make an error, that, for example, the null is true, but you decide to reject it, or the null is false and you decide to accept it. So those are type 1 and type 2 errors. And alpha, the type 1 error, is more serious, and we set from the get-go what our allowable tolerance is for a alpha error, right? So this creates an asymmetry. So we've set alpha, and we essentially want to devise tests that minimize your beta error. Okay. So a test statistic is a statistic. We were just talking about statistics. So a test statistic is a statistic. Usually you want to know its distribution so you can know how unlikely it is to occur. So let's take a look at an example where I have two coins, a fair coin and a loaded coin. So my null is that I have a fair coin. My alternative is that I have this loaded coin, and I don't know which one I have. So I perform an experiment where I flip it 3 times, and just theoretically, these are the likelihoods of getting 3, 2, 1, or 0 heads. And so the test statistic that I'm going to look at is going to be the likelihood ratio. So the ratio of the chance of getting, of the chance that I get a certain number of heads, given that I have a fair coin, divided by that I have a loaded coin. And you can see that that when you so basically right, so if you have a fair coin, F0 is going to be high, and F1 is going to be low. So this likelihood ratio, when it's small, that would indicate that it's not that likely you have a fair coin, and it's quite likely that you have a loaded coin. So there's going to be some cutoff here. So there's going to be some cutoff where we're going to reject that we have a fair coin if our likelihood ratio is too low, too small, right? So the form of the likelihood ratio test is always we're going to reject the hypothesis when our likelihood ratio is less than some cutoff. How do you find that cutoff C? Well, you use alpha. So we fix our type 1 error alpha. Again, alpha is the probability that you reject a null when the null is true. Rejecting the null means that lambda is less than C. And so to find out what that cutoff is, in this case, you would go to the null distribution. The null distribution is the distribution the distribution when the null is true, right? So that's F0 in this case. So these are the probabilities that we get 3, 2, 1, or 0 heads. So if alpha is set to be 0.5, for example, then we would reject if we are if our lambda here is here. I'll just draw a line here, right? So we would reject if our lambda is less than 1.984, right? So alpha is the probability that you reject when the null is true. So above the line that I just drew is the probability that you reject when the null is true. In other words, the probability that I get more than one head is 0.375 plus 0.125. So here I can just sort of make a picture if that's helpful to you. So here I just show in the orange the null distribution, and in purple the alternative distribution. So you can see kind of their ratios by how relatively high one is to the other. And so we have a rejection region and an acceptance region as shown here. Lastly, I introduced the power of a test. So the power is 1 minus beta. So beta is the type 2 error that you that you accept when the null is false. And so again, this is something that we want to maximize because we want to minimize our beta error. And you can compute the power just by using the definition of beta, and to find to find the probability that lambda here is less than 1.984, we use the second column here, which is the alternative distribution, right? And so 1.984, less than 1.984 means that we add up the first two entries here, 0.343 and 0.441. And that gives us 0.784. So we want